Alrighty, lads and ladies, welcome back to Pre-Calculus. Today is going to be a fun day because we're going to be talking about laws of logarithms. And if this is, there's one thing that I think gives people in the previous class, college algebra, a big headache. It's this stuff. And today, here, we're going to conquer that shit. We're going to get you to a place where you are rock stars with it. There is a new homework opening up today that is just on these laws of logarithms, and that is going to be due on Thursday. I'm trying to trim it down right now and make sure I just kind of put the bare essentials in there, but still give you enough practice. It's a little bit tricky to balance. But yeah, that's all. So there's going to be a new homework today on laws of logarithms. It's going to open just after class, and it will be due on Thursday. And then on Thursday, we're going to start talking about logarithm and exponential equations. So make sure you stay on top of that stuff. Before we get into the material, I also want to talk a little bit about the test. Most of your tests are graded. I'm still working through some of the makeups and some of the tests that were taken at the testing center. But the vast majority of you, your tests are now graded. And is Justine here? I wanted to apologize to her about something. She is. Yeah, Justine, please don't panic. I sent you a Canvas message earlier saying like, I can't see some of your written work or like it's missing. I don't know why, but the iPad that I'm using to like get in there and mark things up just wouldn't let me like look at the stuff past the first page. But when I loaded it on the computer, it showed up fine. So I'm sorry about that. Totally not your fault. Everything is fine there. Is class canceled on Thursday? Is there a holiday on Thursday? Is it Veterans Day?
Yeah, it's Veterans Day.
Yes, I think the college is closed on Veterans Day. That's a bummer. Let me triple check your syllabus because I did put all the college holidays in here. Yes, so that does mean we won't have class on Thursday. That's a bummer. It's gonna mess up our schedule a little bit. Well, I'll have to think about what we're going to do with that. So definitely the plan was just laws of logarithms today, and then we can start on equations Thursday, which would have us on track to take the test next week. But if we're going to lose Thursday, then that is going to delay things a little bit. So yeah, college is closed. That means I can't make you guys come to class, obviously. No class on Thursday. And we'll have to wait until next Tuesday to start on the exponential equations and stuff. But there's nothing that's going to stop us from talking about laws of logarithms today. So let's get into that. This is MAC 1140, section number 008, which is pre-calc. And today is the 9th, the 9th, yeah. 2021. And this is section 4.4. Okay, so yeah, there will not be class on Thursday, and that means that probably I'll have your laws of logarithms homework go through till Tuesday instead of having that due Thursday. And we'll begin on exponential and logarithm equations on Tuesday. That might mean we need to push the test a little bit, but I'm not trying to push it too far. So I'll give you the date of the next test. Let me look at the calendar, actually. I don't like the idea of testing you on something with just like 2 days between the last exposure material and the test, but if we can't do it if we can't have class on the 11th, then putting the test on the 18th would be rough. So the plan was to finish the material for the test on Thursday and then have the test be next Thursday, which is the 18th. And that gives us 2 weeks to talk about systems of equations and matrices, which is already a little tight. And if we push it back further than that, that's going to be bad. So I think we're still going to have test 3 on the 18th. So probably, let me go ahead and let's come over here. We're going to have to think on our feet a little bit. So the college is closed for Veterans Day. this Thursday. I think probably what I'll do then is record a lecture for you guys. I'll record the exponential and logarithm equation lecture, and I will post it for you. You can watch it anytime you like, but definitely before Tuesday of next week.
I was actually thinking the same thing.
Yeah, I think it's the only way to make it work, because we have limited time. If we had an extra 2 weeks in the semester and I could just push things around, I would. But I'll record and post the lecture, which would be Thursday, which we'd have on Thursday. And I will post the associated homework. To other sign. Really, the only reason I'm insisting we do it this way is because exam 3 needs to be next Thursday. Which is, we said the 18th, right? Yeah. So exam 3 is just on exponentials and logs, right? Just the stuff that we've done since stopping rational functions. So it's going to be on like exponential functions, their graphs, logarithm functions, their graphs, and then the algebra properties of exponentials and logs that we're going to start talking about today, and exponential and log equations. I will post a quiz. To WebAssign this Thursday. To help you prepare for the test. Okay, so please take note, exam 3 is going to be next Thursday, even though we're losing a day this week. It does mean you have to do a little bit of independent work. The thing that we'd normally do would have a regular lecture this Thursday. Instead, I'll record the lecture and post it. I know that's not quite the same because you don't get to ask and answer questions, but we got to make it work. And it's not that bad. This is material that you guys have almost all seen before in college algebra or high school. Of course, I do have office hours if you ever want to talk about something. If the recorded lecture feels you leaving a little bit empty, don't hesitate to come by office hours and we can run through all the material in person too. Okay, so that's kind of our roadmap, right? The next week or so, we're going to finish up the logs and exponential stuff. Then next Thursday, a week from this Thursday, we will have the third exam. And that third exam will cover just exponentials and logs. And then in the remaining 2 weeks of the class, we're going to talk about systems of equations and matrices. That will be the bulk of the rest of the class. There are 2 other topics that I would like to get in here at the end of the semester, and those are sequences and series. And conic sections. Now, conic sections has always been the section that I'm comfortable kind of squeezing out if we have to, because it really isn't relevant to calculus. But sequences and series, we do need to introduce that notation. So probably the last week and a half of class, we will do systems of equations and matrices. And then that last day of class, I'll show you some notation for sequences and series and maybe give you a little worksheet or something to play with between then and the final. So that's our roadmap. Let's get to the material for today. We have the following rules for exponents. Remember, we reviewed each of these rules for exponents as we started the current chapter. Those were like a to the x times a to the y is equal to a to the x plus y. Then we had a to the x divided by a to the y is equal to a to the x minus y. And a to the x all raised to the y is equal to a to the x times y. Each of these has a corresponding rule for logarithms. Which your book calls logarithm laws. So the logarithm law that corresponds to this first exponential rule is the base a logarithm of a product of two numbers is equal to the base a log of the first number plus the base a log of the second number. So kind of you can think of this first rule for exponentials as saying an exponential takes multiplication outside and turns it into addition inside. The corresponding rule for the inverse function is that it takes multiplication inside and turns it into addition outside. Kind of cool, right? There's like a nice duality here. The corresponding rule for the second exponential statement is that if you have the base a logarithm of a ratio, something like log base a of x over y, this is the same as the base a log of the top minus the base a log of the bottom. So exponentials take division outside and turn them into subtraction inside. And logarithms take division inside and turn them into subtraction outside. And then finally, and this is maybe the most important one, the log base a of a power x to the y. So here, this takes powers outside and turns them into multiples inside. We would expect this to take powers inside and turn them into multiples outside, and that's exactly what it does. This is y times the base a log of x. And these things over here are your logarithm laws. And we need to burn these into our brain. Among other things, these are useful for solving equations. And you'll see in Calc 1, when you talk about something called logarithmic differentiation, also very useful for certain calculus operations. For us, though, they're just algebra statements that we need to practice with. So I'm going to just run through a few basic problems where we kind of practice using these guys, either to evaluate logarithm statements or to expand or contract logarithm statements. Before I move away, though, there is one more thing. There's also something called the change of base formula. And this is more useful from a calculation perspective. So these are your log laws. And then the change of base formula says this. If somebody hands you, say, the log base b of x, and you want to change that to some other base, like the base c logarithm, you can do that. That's the same as the base c log of x divided by the base c log of b, the old base. This is especially useful for calculators. If you take this new base, c, to be either e or 10, what that means is you can take any base logarithm, like the base 2 or base 3 or base 10 log, base 5 logarithm, whatever, and change it into a natural log or a common log. So the special cases would say that the base b log of x is the ln of x over the ln of b, or that the base b log of x is the log, common log of x, over the log of b. And if you look on your calculator, your TI-30, you have an log button and you have an ln button. So you can use this change of base formula with c equal to e to turn any base logarithm into a ratio of natural logs, or turn any log base whatever into a common log. All right, let's get some practice with these. I'll grab some examples from your book. Here we go. So what if I want to calculate or evaluate without a calculator something like the base 4 log of 2 plus the base 4 log of 32. I'll give some space here. We could also look at something like the base 2 log of 80 minus the base 2 log of 5. And leave some more space for the negative 1/3 base 10 log of 8. Let's see. Actually, this last one might require a calculator. Let me change that to the base. I'll leave it. I'll leave it. Calculator okay on part C. So the base 4 log of 2, we could actually calculate, right? What power of 4 is equal to 2? This is kind of similar to some of the stuff we did on the first day we talked about logs.
1/2.
Yeah, 4 to the 1/2 is 2. So the base 4 log of 2 is 1/2. You might be able to get there with 32, but since 32 is an odd power of 2, not an even power of 2, it's 2 to the 5, it's not going to be as clean here. So what I would recommend is combining these using that first log law. So I can write this as the base 2 log of 2 times 32. I'm sorry, base 4 log, base 4 log of 2 times 32. And 2 times 32 is 64. And 64 is a clean power of 4. 64 is 4 raised to the what? What is the base 4 log of 64?
Is it 3?
Let's see. Yeah, 4 cubed is 64, right? 4 times 4 is 16, times 4 again is 64. Yeah, so this is 3. And the big trick there is combining with the first log rule, or log law. So the addition outside becomes multiplication inside. That's the nice feature of logarithms. All right, which log law sounds kind of like, you guys watch Arrested Development, Bob the Loblog. Sorry, my tongue is tied now. Bob Loblaw's Loblog. Which log law should we apply to this statement?
Second one.
Yeah, the second one. Really quick, I'll ask down here, question mark, is this equal to log 2 of 80 divided by log 2 of 5? Is that the correct way to apply that rule?
No,
No. What is the correct way to apply that rule?
log 80 over 5.
Yeah, it would be the log base 2 of 80 over 5, right? So 1 log with the division inside. That's how that works, right? Subtraction outside, difference of 2 logs, is 1 log with the division inside, which is not the same as this. And it's a very common mistake to write the logarithm upstairs and downstairs to confuse this for this. So make sure you understand the difference. Why is this helpful? Well, what is 80 divided by 5?
$16.
Very good. So while the base 2 log of 80 on its own is a nasty irrational number, and the base 2 log of 5 on its own is a nasty irrational number, when we combine these two things, the inside becomes 16, and 16 is a nice power of 2. So this is an integer. What is the base 2 log of 16?
4.
4. Yeah, 2 to the 4 is 16, right? 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16. So the base 2 log of 16 is 4. All right, this last one, I'm not sure why your book groups this in with the other examples here. We can use one of our log laws on this thing, but the result won't be super nice to calculate afterwards. Which one of the log laws can I apply to this expression?
The third one.
Yeah, that third rule says that powers inside are the same as multiples outside. And you could read that left to right or right to left. I would say here that this is the same as the log of 8 raised to the negative 1/3 power. And what is 8 to the negative 1/3? This is the log of what? Well, 8 to the negative 1/3, that's 1 over 8 to the positive 1/3. And then 8 to the 1/3, that's the cube root of 8. What is the cube root of 8? What is this downstairs?
2.
Yeah, good. So this is the log of 1/2, which is the base 10 log of 1/2. And that's not a nice number. But if I want to evaluate this, I can with my calculator, right? So if we take I don't have a TI-30 emulator here, unfortunately. I do have an 84 emulator. Come on. There we go. All right. So on your TI-30, if you hunt around, you'll find you have a button that says log and a button that says ln. And if I want to evaluate this, I would type log of 1 divided by 2, and then close that parentheses. Always use good notation. And that's about negative 0.301. All right. So the log laws can help us calculate expressions that are hard to find individually by first combining them. And then, if you're lucky, that will make the inside a clean power of the base. In some instances that won't happen, but it's still good to know how to operate with these rules, that you can bring this power inside. Really, the reason we practice with these laws, I mean, there are problems like this out there for sure, but they're a little bit contrived. Really, the reason we practice with these is because at some point, we're going to start solving equations by taking logarithms on both sides. And when you do that, depending on the complexity of the equation you start with, you may end up with a log of a bunch of shit inside, like all multiplied together. Maybe some of them variables, some of them numbers, maybe raised to some powers. So what we want to do is practice expanding and combining logarithm expressions. So I'll say here, expand each log expression. We're going to start with the base 2 log of 6x, then the base 5 log of x cubed times y to the 6, then the natural log of something like ab over the cube root of c. And your book doesn't have it, but I want to add one more here. Let's do the ln of x squared over the square root of y times z cubed. And just to be clear here, only the y is under the square root downstairs. All right. So which of the rules can I apply here, and what do I get?
Would it be the first one?
Yeah, right. This is a logarithm with some multiplication inside. So I can use that first rule to turn the multiplication inside to addition outside. This would be the base 2 log of the first thing plus the base 2 log of the second thing. So multiplication inside becomes addition outside. The next one, we're going to start the same sort of way, right? I've got some multiplication inside, which I can turn into addition outside, but then each of the things has a power. So after we expand this using the first rule, that'll give me log base 5 of x cubed plus log base 5 of y to the 6. We still have some work we can do. What more can I do with this? Say just this piece.
Would you take this 3 and put it in front of the log?
Yeah, exactly, right? Our third property says that a logarithm of a power is the same as that power times the logarithm of the base inside. So kind of powers inside can come down in front. But you have to expand first, right? Only the x is being raised to the 3, and only the y is being raised to the 6. So I can't bring the power down until I've split those up. But once they're split up, the power can come down from each. Like so. Good stuff, right? And you might start to get a whiff of why this would be so useful for solving exponential equations. This ability to bring a power down using a logarithm is incredibly useful. All right, these last two are a bit more involved. So if you look at the inside of the logarithm here, what sort of appears to be the outermost thing going on? Like you've got some multiplication upstairs, you've got a power or a root downstairs, and we've got this division here. Where would you get started trying to expand out each of those things?
Would you use the second law to split it up?
Yeah. Yeah, I like starting with this division. So inside there, I've got AB divided by the cube root of C. So I would start by saying that's the natural log of AB minus the natural log of the cube root of C. And that's using the second law, like Jimmy said. Now using the first law, I can expand the ln of A times B as the ln of A plus the ln of B. And using the third law, I can take this guy. Remember, the cube root of C is the same as C to the 1/3. So this minus is this minus. And then the ln of the cube root of C is the ln of C to the 1/3. So that's 1/3 times the ln of C. Any questions so far? Okay. For this last one, the reason I chose to add this here is because we have two separate terms downstairs, and this can be a little bit confusing. I still think it's wise to start with the division inside and turning that into subtraction outside. So this looks like the ln of x squared minus the ln of, I'll write this as y to the 1/2 times z to the 3rd. This 2, of course, can come down. This is 2 times the ln of x. And then this minus is this minus. Now watch me here. I'm going to take this natural log and expand it, turning the multiplication inside to addition outside. But when we do that, we need to be very careful that both of the terms get this negative. I say this, and then on the test, I always end up taking off points in a bunch of places because it's so easy to miss. Put some big parentheses here. And you have ln of y to the 1/2 plus ln of z cubed, like this. Because both of those terms were downstairs in the original logarithm expression, they both need to get this minus sign. In other words, we're subtracting this whole thing. And since this whole thing is this sum of two terms, we're really subtracting each of these terms. So when you expand a logarithm, the parts that come from the denominator of the inside, make sure that you put these in parentheses to ensure that everybody gets the negative. Kind of the check that you can use for this is that in the expanded version, every term that came from the downstairs should be negative, and every term that came from the upstairs should be positive. Now, pulling down the powers and distributing the negative, we get 2 ln x minus 1/2 ln y minus 3 ln z. The typical error here is to not put these parentheses and to give me this with a plus rather than a minus, which would be incorrect. That would mean that the z cubed was upstairs originally, which it is not. Are there any questions about any of these? Okay. Of course, you can run all this stuff in the other direction, right? I could give you this and ask you to combine it into this. I could just give you this and say combine, right? And hopefully you arrive at this. Let's take a look at a few examples of that nature. So this would be 3, we'll get 3 times the log of x plus 1/2 times the log of x plus 1. 3 times the natural log of s plus 1/2 times the natural log of t minus 4 times the natural log of t squared plus 1. And yeah, we'll stick to this. This is okay. These aren't really missing anything important. So what do I do here? I want to combine these into a single logarithm. That means I need to run the processes we were just doing, but in reverse. What would your first step look like if I want to get these into a single log?
You have to multiply them.
So I like what John says here. We've got this addition outside, which means we're going to end up with some multiplication inside. But there's something I would want to do before that. If you look at these last few examples, imagine running exactly these steps backwards. So
Did you do
here,
the third
the
one?
last thing we did was pull the powers down. And then we did the multiplication inside to addition outside. And then we did the subtraction outside to division inside. So we want to run these exactly in reverse. In other words, in order to use that addition outside is multiplication inside rule, I have to just have the log of something plus the log of something. I can't have these constants here. So before I can push them together with multiplication inside, I need to pull those constants in. So what would this term become? If I pull that 3 inside the log.
Log x to the cubed.
Very good. The log of x cubed. And similarly, this guy is going to become the log of x plus 1 to the 1/2, or the square root of x plus 1. And now that I have just log of something plus log of something with no numbers out front, now I can push those together into a single log with the insides multiplied. Like so. Right, and it's important we bring the constants in first as powers, because if we tried to bring them in later, we would end up with something weird, right? The x plus 1 and only the x plus 1 is supposed to be raised to the 1/2 power. This guy doesn't have a 1/2. And similarly, the x here and only the x here is supposed to be raised to a 3. There's no 3 anywhere over here. Let's try the same thing, but with this guy. It's very similar, just has more terms. So this is 3 times the natural log of s plus 1/2 times the natural log of t minus 4 times the natural log of t squared plus 1. So first I bring in these multiples as powers. So it's going to be the natural log of s cubed plus the natural log of t to the 1/2, or the square root of t, minus the natural log of t squared plus 1 all to the 4. And another place where you want to be careful with your parentheses, right? It's the whole inside of this logarithm that's going to get raised to the 4. So you really do have to put t squared plus 1 in those little parens and then raise it all to the 4. Without those little parens, this wouldn't be correct. And another quick note, I know where the sign doesn't do it, but always put the inside of your logarithms in parentheses. I wouldn't want to write just ln square root t without these parens. Certainly wouldn't want to just write ln t squared plus 1 without the parens, because then you can't tell if the plus 1 is inside or outside the log. So just good discipline. So now these first two, I have the ln of something plus the ln of something else, no constants out front. So I can combine these into a single log using my Addition outside is multiplication inside rule. The ln of this plus the ln of this is the ln of the first thing times the second thing. 1 log. And then I still have minus ln of t squared plus 1 to the 4. So finally, I can use my subtraction outside is division inside rule and write this as the ln of s cubed times the square root of t, all divided by t squared plus 1 to the 4. Any questions on these projects? Oh, I see there's something in the chat there. Did we solve the 5? Simplified it all. I apologize. So this is an S. I should not a 5. I'll try to make it look a little more like an S down here. Is that what you're asking about? Okay, good. No worries. Yeah, I don't like using the variable S, especially not a Latin S, because it looks so much like a 5. And I see how that could be confusing. But this is the 3 times the natural log of S. So we brought the 3 inside as a power, and it became the natural log of S to the 3, similar to what we did with these guys. All right. I would like to kind of bring us full circle now, if that's okay, by reminding you how we started talking about logarithms. So the very first conversation we had about logs began by looking at an equation. And that's where we're moving. So since we have the time here today, I will go ahead and start introducing section 4.5, which is our very last section on exponentials and logs. All right, we probably won't get through the whole thing here today, and I'll post that video on Thursday for you with the remainder of this. But since we do have time, let's talk about it. I'll say recall. All this log madness began by thinking about the equation 2 to the x equals 3. We're ready to solve this now. If I begin with 2 to the x equals 3, this can actually be solved a few different ways, but all of them require one step, one crucial step, which is called taking logarithms. What that means is you're going to take both sides, the left and the right-hand sides, and shove them inside some logarithm. It's like squaring both sides or taking the square root on both sides. Only here, instead of taking the square root on both sides, you're going to take the logarithm of both sides. It's actually up to you what base logarithm you use. First time here, I'll use the base 2 logarithm. Why? Because I have a base 2 exponential. So I'm going to take the base 2 logarithm on both sides. That will give me the log base 2 of 2 to the x on the left, and the log base 2 of 3 on the right. And then one of the very first properties of logarithms we talked about, not today, but last time, and maybe the time before as well, is that the base a log of a to some stuff will always just be that stuff. In other words, the base 2 log of 2 to the x, that's just x. So this is the base 2 log of 3. And if I open up a Desmos window and ask it for the base 2 log of 3, typing log underscore 2 of 3, it'll give me that number that I gave you guys the other day, right? 1.58496-ish. So this is how you solve the most basic form of exponential equations, which is like a to the x equals b. And we could have used any other base log also. For example, if I start with 2 to the x equals 3, and I take the ln of both sides, then I get the ln of 2 to the x equals the ln of 3. Now the ln of 2 to the x, it's not quite as nice as the base 2 log of 2 to the x, because the base of the ln function is e, not 2. They don't kind of cancel perfectly. But what does our third log law tell us about this piece, the base, the natural log of 2 to the x? Anybody help me simplify the ln of 2 to the x using the log laws we talked about earlier today?
It'd be x times ln to the 2.
Perfect. X times the natural log of 2, right? That's when I said that that third law is the one that's most useful for solving equations. This is what I mean. So the x is a power inside, so he can come down as a multiple, and you get x times the ln of 2. And on the right-hand side, we still have the ln of 3. And at a glance, it might look like we're going to come up with a different solution. Here now I have x times the ln of 2. ln of 2 is just a number. It's like 0.69. I joke with my Calc 2 students that it's easy to remember because, like, 69, nice, right? For some reason, it sticks in everybody's head. So ln of 2, like 0.69. It's just a number. Don't be afraid of it. Just a number. If I want to solve this equation now, I've got the thing I want, x times some number equals some other number. So you just divide over by the natural log of 2. You get x equals the ln of 3 over the ln of 2. And this raises the natural question, is this answer the same as this answer? And we've already seen today the tool that will allow us to answer that question. So without putting it in a calculator, are these the same? I certainly hope so. Otherwise, mathematics is deeply broken. Remember the change of base formula? So the base 2 log of 3, base b log of x, base 2 log of 3, would be the same as the natural log of 3 over the natural log of 2. These are the same by the change of base formula. So yeah, same thing, same value. When we talk about solving exponential and logarithm equations, you'll often be asked for your answer in one of, or maybe both of, two forms. Either the exact answer in terms of logarithms, and you could give me this or this for that exact answer, or a decimal approximation, right, like 1.58496. If you're asked for the decimal approximation, you should just use the natural log to get there, because your calculator has an ln button. It doesn't have a log base 2 button. In fact, as I solve these equations for you, I will always use the natural log. I don't see any purpose in using the base 2 logarithm or the base 7 logarithm, in the same way that I don't care about the base 2 exponential. I really just care about the base e exponential. This is almost the whole story for exponential equations, by the way. They can pretty much all be managed in this fashion. The trick is, for some of them, taking whatever it is they give you and getting it down to something like this. That's not always obvious. So before I let you go, let's look at some examples. Maybe I'll add these into your homework. We'll just extend that homework to the next Tuesday, and it'll have laws of logarithms and the equations. That's what we'll do. That will work well. Your test will be next Thursday. All right, so let's solve. 3 to the x plus 2 equals 7. If 7 were a nice power of 3, then maybe I could get away without using logarithms, right? Like if this was at 27, then I could say, oh, 3 to the x plus 2 is equal to 27. That means 3 to the x plus 2 is equal to 3 to the 3. So x plus 2 is 3. But most of the time you won't be able to do that. Most of the time you really will need logarithms. So it's, I think, not an unhealthy approach to just assume you're going to use logs when you encounter an exponential equation. What makes an exponential equation exponential is that the variable is in the exponent. So my first step here is going to do what?
Choose a base of a log for the equation.
Yeah, very good. I need to take logs on both sides, right? And so, yeah, we choose the base. I'll tell you, I'm always going to use the natural log. The natural log is just the nice one to use. You could use the base 3 logarithm if you wanted. But at the end, if you need a decimal approximation, the only way to put a base 3 logarithm through most calculators is to convert it into a natural log anyway. So we might as well just use ln. So first we will take ln of both sides. This gives me the ln of, and again, be careful with your notation. Make sure to put the inside of the logarithm in parentheses. Was the ln of 7. Now, the ln of 3 to the x plus 2, I've got this whole power here. So he can come down as a multiple. This is x plus 2 times the ln of 3. And I'm putting the x plus 2 in parentheses because it is a single chunk coming down in front here. It's not just 3 to the 2, it's not just 3 to the x, it's 3 to the x plus 2. So I need to put that x plus 2 in parentheses. And then on the right-hand side here, I have the natural log of 7. So kind of the magic of the logarithm is that it takes exponential equations and turns them into linear equations. This, although the numbers are weird, is a linear equation. I can distribute the x plus 2, and I get x times the natural log of 3 plus 2 times the natural log of 3 equals the natural log of 7. Remember, our goal is always to get x alone. So I would want to subtract this term over to the right and then divide by the natural log of 3. Doing just one step at a time, always being very careful. I get x times the natural log of 3 is equal to the natural log of 7 minus 2 times the natural log of 3. And that means that x has to be the natural log of 7 minus 2 natural log of 3, all divided by the natural log of 3. Can I cancel the natural log of 3's here? Can I cancel the ln's?
Yes. Yes.
So the answer to both of those questions is no. I can't cancel the natural log of 3 because the natural log of 3, well, it shows up here, doesn't show up over here. Remember, I need to be able to factor something out in order to cancel it. And I can't cancel the ln's because this ln, this is not multiplication. This isn't ln times 7. It's ln of 7. This is not ln times 3. It's ln of 3. So in the same way, you can't like cancel a square root, right? If I've got the square root of 7 minus the square root of 3 all over the square root of 3, I can't just like say the square roots go away. Same thing with the natural log. If you wanted to clean this up, the only thing you could really do, you could split up the fraction and then in the second piece, cancel the natural log of 3. So you'd get the natural log of 7 over the natural log of 3 minus 2 natural log of 3 over the natural log of 3. So we cannot cancel the ln's. This is not 7 over 3. I can cancel natural log of 3 over natural log of 3. Right, those are each a number, and they are the same number. So this is the ln of 7 over the ln of 3 minus 2. But if you give me it like this, I would be perfectly happy. There's absolutely nothing wrong with this. When in doubt, be cautious, right? It's better to stop a little bit short on your simplification than to make a mistake and give an incorrect result. Okay. I'll look at maybe just one more example, and then I think I will let you guys go. Or maybe 2 more examples. Yeah, let's do 2 more examples. We'll hold off on logarithm equations for now, just exponentials. So I'd like to solve 8 times e to the 2x equals 20. And remember, our goal is always to get this into the form a to the something equals b, like a to the x equals b, something like that. So the e to the 2x is not a problem. If I just had e to the 2x equals 20, I would start by taking logs. But I've got this 8 over here in the way. I need to get rid of him first. You want to isolate the exponential, then take logs. So before I take any logarithms here, I would rewrite this as e to the 2x equals 20 over 8. Well, these are both divisible by 4. So I could say this is the same as e to the 2x equals 5/2. And now I can take logs. So isolate the exponential term, then take logs. Here's the magic step. I take the natural log of both sides. What is the natural log of e to the 2x?
Is it 2x?
It is, right? And you can think about this two different ways. You can pull the 2x down in front, and you'd have 2x times the natural log of just e, and then the natural log of e is 1. Or you can appeal to that property from our previous lecture, where we said that the natural log of e to some stuff will always just be that stuff. Either way, the left-hand side simplifies to just 2x. And the right-hand side is the natural log of 5/2. And now to finish this up, I divide both sides by 2. So I get x equals the natural log of 5/2 all over 2, which is the same as 1/2 times the natural log of 5/2. Quick question. Is this the same as the natural log of 5/4? Can I multiply this and this? Or like, can I divide this and this?
No.
Yeah, they're not, right? So one of the things that can be tempting with logarithms to try and invent rules or like things that look like they might work based on the notation, but be very, very careful and make sure the only manipulations you're doing with logarithms are exactly those specified by the properties of the laws. If you're ever uncertain, you can check with your calculator. So if I look at the ln of 5/2, close the parentheses, then divide by 2, this is the answer to my problem, right? That's this guy is approximately equal to 0.4581. I can verify that that's the same as 1/2 times the natural log of 5/2. Okay, so this way of writing things was kosher because I get the same thing, right? Whether I write it as ln of 5/2 all divided by 2, that gave me the 0.4581, or I write it as 1/2 times the ln of 5/2, that also gives me 0.4581. But then if I see if I can shove that 1/2 inside and write it as the ln of 5/4, I get something completely different, 0.22314. So certainly they are not equal. So from the calculator, both of these are 0.4581, but this guy is 0.2231-ish, right? Approximately. So either of these is totally kosher. These would be the exact solutions. These would be the decimal approximation, and neither of these is correct. Cannot do that. All right, I have one more example to show you, and then I'll let you go. Sometimes, maybe I lied, maybe 2 more examples. We'll see how it goes. Sometimes we have to do some slightly trickier algebra before we can turn our equation into the sort where we take logs. Let's start with this guy. We want to solve. So this looks kind of complicated. I've got variables in the exponent. I've got variables out of the exponent. And it's not immediately obvious how to isolate an exponential term or any other term. The right-hand side is 0, and that kind of gives us a hint. What do you usually do if you've got everything pulled onto one side and the other side is 0? What's usually your next step? Thinking back all the equations we've solved this term. Starts with an F.
Factor.
Yeah, factor, right? Are there any common factors here? Well, definitely there's a common factor of e to the x. If I factor out the e to the x, I get 3x plus x squared. And then here, the 3x plus x squared, that can be factored also. This is x times x plus, I'll write it like this, x times 3 plus x times e to the x equals 0. And then by your zero factor property, the same thing that we've been using when we work with polynomials, this means x has to be 0, 3 plus x has to be 0, or e to the x has to be 0. X equals 0, okay, great, there's a solution. 3 plus x equals 0, that means x is negative 3. There's another solution. E to the x equals 0. Can I do anything with that?
No.
Yeah, that's correct. No, I really can't. The graph of e to the x, remember, looks like this. And one of the properties of e to the x, we said, was that it's never 0, right? It's always strictly bigger than 0. If you wanted to try, sort of the natural next step here would be to take natural logs. You'd say the ln of e to the x is equal to the ln of 0. And the ln of e to the x is just x. So that would mean x is equal to the ln of 0. But what is the ln of 0? This is undefined. Remember, the domain of the natural log is just positive numbers. 0 is not positive. So e to the x equals 0, this gives us no solutions, either thinking about the graph, thinking about this property, or saying that the natural log of 0 is undefined, any of those approaches. So your two solutions here are just 0 and negative 3, right? X equals 0 and x equals negative 3. So sometimes you have to factor. You have to work with the equation algebraically a little bit before you can do any of the stuff related to the exponentials. There's a slightly deeper trick that also involves some factoring. Here, the factoring is not quite as obvious. Certainly, there are no common factors here. But by one of our properties of exponents, e to the 2x is the same as e to the x all squared. So this is e to the x all squared minus e to the x minus 6 equals 0. And you can kind of think of this as like u squared minus u minus 6 equals 0. You can think of this as a quadratic in e to the x. And you can rewrite this as u squared minus u minus 6 equals 0 if you want. Some people prefer to factor straight from here. Some people prefer to write down the substitution. Either way is fine with me. This you could then factor using the AC method. I need two numbers that multiply to -6 and sum to -1. That would be -3 and +2. So we see that either u is equal to 3 or u is equal to -2. But what was u? U is e to the x. So this means e to the x is 3 or e to the x is -2. One of these will give us a solution. One of them will not. Which one does not give us a solution? Think about what we said here. Which one of these two doesn't give us a solution? Yeah, very good. The second one. The second one does not give us a solution. This guy has no solution because e to the x is always greater than 0. It's never equal to -2, right? E to the x can never be -2. E to the x is always positive. But this guy, if I take the natural log on both sides, I get the natural log of e to the x is equal to the natural log of 3, and that means x is the natural log of 3. So that is the only solution to this equation, natural log of 3. All right, this is where I'm going to stop for today. The video that I will post for you guys on Thursday as a replacement for the class we're going to miss due to Veterans Day, which you can watch whenever you like, is going to be on solving logarithm equations. So rather than starting with like some exponential stuff and solving for x, we're going to start some logarithm stuff and solve for x. It'll be fun. But you want to practice this stuff first. So I'm going to post a new homework set for you guys today. It will have 4.4 and 4.5 part 1 in it. 4.4 is on using those log properties to expand and combine. And then 4.5 part 1 will be exponential equations. I'd like you to practice those as much as you can between now and Thursday. Don't wait for like the weekend or God forbid Monday to start on this homework. It's going to be a big one because you're going to have another homework set opening up on Thursday as along with the video lecture I'm going to post. And in addition to that, there will be a quiz. Remember, your exam 3 is a week from this Thursday. So that's the 18th. So just be mindful of that. If you're behind on homework, please make sure you get caught up. Don't wait. And if you need anything from me, just reach out. You know how to find me, right? Canvas, Discord, or email. Office hours, Monday, Wednesday, Friday, 1 to 2. If you need to meet with me outside that, we can. Tuesday, Thursday from like 10 to 11 has kind of been the standard time for me to do those extra meetings. So if you're available for any of those, just let me know. That's it. I'll see you guys, I guess, a week from today. So hang in there. Make sure you're working hard. And if you need anything, don't hesitate to reach out.